Right, we're going to do a little chill lesson on series and sequence. This will come up later in the course, but you need to see some of this notation before we get there. Okay, so a sequence is just an ordered list of numbers that follows a pattern. And then we know two special types of sequences called geometric and arithmetic, which are just basically linear and exponential growth patterns. Okay, so the way we label the terms in a sequence is the first term is labeled A sub 1, the second is A sub 2, or whatever the sequence name is. So B sub 3, okay, we're using A, so A sub 3, A sub 4, and then this it would A sub n is the nth term in the sequence, okay? And I can see that the pattern, the growth rate is we're adding 2 each time. So that would be my common difference. So the formula for this arithmetic sequence or this linear function would be the nth term would be calculated by the slope, which is the common difference, times the term number. But since really this is our initial value, we need the input to be 0. So we're going to have to take our n, subtract by 1, and then add our initial value at the end, a sub plus a sub 1. Okay, so next up is a geometric sequence. I can see that I'm timesing by 2, and I have terms a sub 1, a sub 2, a sub 3, a sub 4, and then a sub n, or the nth term. Okay, and so the formula for a geometric sequence is a sub n is equal to my initial value, so a sub 1, times our common ratio, which we'll call r, raised to the, and then we want a sub 1 to have an exponent of 0 since it's our initial value. So we're going to have to use n minus 1, and that's it. Yeah. So you just have to be a little careful if you're starting with a sub 0 or a sub 1. Okay, so if you're saying that your n value, your first term is 1, then you, to account for the shift, you just have to subtract 1 in your exponent. Okay. Let's do a little practice with writing the first 4 terms of the sequence. We're given the nth term, a sub n is equal to n 2 to the n over n factorial. So a sub n is equal to 2 to the n over n factorial. So we are going to plug in 1 for n. So 2 to the 1 over 1 factorial is equal to 2 over 1, which is 2. Okay, a sub 2 is equal to 2 to the 2 over 2 factorial, which is 4 over 2 times 1. So that's equal to 2. Okay. Oh, I know what I did wrong here. I said we're going to begin with 0. So let's go ahead and begin with 0. And yeah, oops. Okay, so a sub 0, that's our first term, is 2 to the 0 over 0 factorial. 2 to the 0 is 1, and actually 0 factorial is also 1. So 1 over 1 is 1. And then our last term, a sub 3, is equal to 2 to the 3 over 3 factorial. So 2 to the 3 is 8 over 3 times 2 times 1, which is 8 over 6, which is 4 over 3. Okay, so our sequence would list as 1, comma 2, comma 2, comma 4 thirds. All right, and if it goes on forever, we would just put the dot, dot, dot. All right, so let's practice a little bit with factorials. we just want to simplify these. So 8 factorial over 2 factorial times 6 factorial. I'm going to go ahead and expand them, though you probably are going to get the gist after we do this. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 6 times 5 times 4 times 3 times 2 times 1. And we see that anything, the only parts of the 8 factorial that get left are the 8 times 7. And then there's nothing to cancel with the 2 factorial. So we end up with just 8 times 7 over 2. So 56 over 2, which is 28. Okay, so a lot of the factorial stuff cancels out. So now let's go to n factorial over n minus 1 factorial. I'm going to expand going from 1 up this time. So let's just pretend I'm just going to say 1 times 2 times 3 times 4 dot 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 times n minus 1. So one number before n times n over 1 times 2 times 3 times 4 dot 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 times n minus 1. The only number that we didn't multiply the numerator and the denominator by was the n. Everything else repeats in the numerator and the denominator. So we just end up with plain n. So if we think about this as like 5 factorial over 4 factorial, we end up with 1 times 2 times 3 times 4 times 5 over 1 times 2 times 3 times 4. Only that one, only the last number in the numerator remains behind. Okay. All right, series. A series is a sequence that is added together. So all we do is take our sequence, our ordered list, 1, 4, 7, 11, and we add them up. 1 plus 4 plus 7 plus 11. Okay, so a series is when we add up a sequence. Okay, so series notation. Oh, so this series right here has an nth term of a sub n is equal to, it looks like our common difference is 3 times n minus 1, because we have to subtract, to get back to 0, plus our initial value, which is 1. Okay, so I can simplify this, giving me 3n minus 3 plus 1 gives me 3n minus 2. So a sub n is equal to 3n minus 2. So the way we would write this in sigma notation is we would say the sum, so we use this sigma, is equal to, and the rule is 3n minus 2. And I want to add up the first, say I want to add up infinity terms, I would say n is equal to 1, because that's the variable I'm using inside my rule. And then the last n value I plug in goes in the top. So I'm going to plug in from integers 1 to infinity. Okay. So here's our series notation, which we also call sigma notation. Okay. And so if I were to read this, a finite series is when we have a partial sum. So we have a limited number of terms. So you can see here that our sigma notation runs from I is equal to 1 to I is equal to 5. And we're plugging it into 3i plus 4. So we're substituting in each number I from 1 to 5 in the rule 3i plus 4, and then we add them up. So if I were to expand this, this would equal 3 times 1 plus 4 plus 3 times 2 plus 4 plus 3 times 3 plus 4 plus 3 times 4 plus 4 plus 3 times 5 plus 4. Okay, so when we're expanding out our sigma, and then we can add that up. When we're expanding out our sigma notation, we hope that there's like not too many values that we have to plug in because it can take a long time for us to expand out the sum. Okay, so again, sigma is the Greek letter for sum. The top variable is the ending value that we're plugging in. The bottom number is the starting value, and then on the right is the rule. Okay. We also can see our sigma notation written like this. So if I have same thing, but instead of 3i plus 4, we just name the function, and then I said that u sub I is equal to 3i plus 4. It's the same thing. You can just substitute in 3i plus 4 in for u sub I. All right, so an infinite series is when there are an infinite number of terms. So our rule is a sub I. So all we're going to be plugging in is a sub 1. So the first term plus the second term plus the third term. But notice that we're going to go all the way to infinity. So we just write dot, dot, dot plus a sub n minus 1 plus dot, dot, dot. And it just keeps going. Okay. Partial sums of arithmetic series, excuse me. So arithmetic, remember, is we have a constant to each term in the sequence, we have a constant additive or a constant difference, I guess. That's a better way. Okay. And we have a formula basically for a partial sum of an arithmetic sequence, and it's this. S of n, so the sum of n terms is equal to n over 2 times the initial term plus the final term. And this is the number of terms. Okay. So let's go ahead and do it the long way. We're going to expand first. So I have 11 times 1 minus 6 plus 11 times 2 minus 6 plus 11 times 3 minus 6 plus 11 times 4 minus 6, which gives me, all right, I'm just going to evaluate this. This is 5 plus 22 minus 6 is 16, plus 33 minus 6 is 27, plus 44 minus 6 is 38, and then I add those up to give me a total of 86. So that's the long way. We expanded and added together. But since I recognize that our rule is a linear growth pattern or a linear pattern, I'm going to use the formula to solve for a partial sum. Okay, so I have S of n is equal to n over 2 times a sub 1 plus a sub n. So I need to know what my n value is. I know that the n value is 4. Okay, so we're going to look up the first 4. We're going to add the first 4 terms of our series. So 4 over 2. And then I need our initial value. So on the side, I'm just going to do a sub 1 is equal to, and our rule is 11n minus 6. So, yep. Okay. So I do 11 times 1 minus 6 gives me 5. Okay. And then a sub n, which is a sub 4, is equal to 11 times 4 minus 6, which I know we already did, but that's fine, is 38. Okay, so I'm just going to plug it into my formula. 5 plus 8, 38. And when I get that, I get S sub 4 is equal to 86. Matchy matchy? Yes, because it's really the same thing. The formula is just a shortcut for us, especially when I do something like this. Ooh, I see that I have an I and an N, so I'm going to go ahead and change my I to an N here. So I have 100 from N, the sum from 1 to 150 of negative 2N plus 1. I don't want to expand this. This is going to take forever. So I'm going to use the rule. Okay. So I get S of N is equal to N over 2 times A sub 1 plus A sub N. I am on the side, A sub 1 is negative 2 times 1 plus 1, which is negative 1. And A sub 150 is equal to negative 2 times 150 plus 1. So I have negative 300 plus 1 gives me negative 299. So S sub N, S sub 150 is equal to 150 over 2 times negative 1 plus negative 299. So S sub 150 is equal to 75 times negative 300, which is negative 22,500. I'm sure glad I didn't have to expand out those 150 terms. All right, up next is a partial sum of a geometric series. So same idea with geometric series, we have a shortcut. So when you recognize that your rule, A times R to the I, or A times R to the I minus 1, if you're starting with 1, okay? Then we can get a partial sum by using the formula A sub 1, or just A, change that in my notes, just A, times 1 minus R to the N over 1 minus R, okay? So we're going to find the partial sum of each of these series. Since they have a limited number of terms, they are a partial sum. So I know that the number on top is my N value. Well, I mixed up my N's and my I's all over the place. So N is equal to 1, okay? And since N is the variable in my rule, I'm going to make sure that the value underneath my sigma notation matches, okay? All right, so because that's the number I'm plugging in. So next up, I noticed that this looks like a geometric sequence. Okay. Okay, so I made a mistake and I shouldn't have put this minus 1 right here. So this should read A to the A times R to the I, and then we'll be okay. Okay, so what I'm going to do is go ahead and substitute in. I'm just going to go ahead and solve for the formula now. So I have S sub N is equal to A times 1 minus R to the N over 1 minus R. So I get 4 times 1 minus 0.3 to the 4 over 1 minus 0.3. Make sure that you raise the 0.3 to the 4 first before you subtract that from 1. So I get S sub N is equal to 5.668 when I plug that into my calculator. All right, next up, I have the sum from 1 to 100 of 3 times 1 over 5 to the n, and that looks like an exponential function or a geometric sequence rule. So my a is equal to 3, and my r is equal to 1/5. So I'm going to write this as 3 times 1 minus, I'm going to use a decimal, 0.2 to the 100. Oh, I forgot to label that as my ending n, over 1 minus 0.2. And when I substitute that in, I get 1.25. All right, so we also can take sums of an infinite geometric series. So when the terms don't end, but there's a condition. It's that the r value has to be less than 1, so the sequence has to be decreasing, okay? So again, we use a very similar type of formula, but instead we're going to have a over 1 minus r. Okay, so I have the sequence, sorry, the sum of 1 to infinity of 4 times 0.6 to the n minus 1. Honestly, we can rewrite this as, if I substitute in 0 to infinity instead, so I subtract 1 from n, then I'm going to adjust my n value by adding 1. So this is now in the same form as we can see in our notes here. So when n is equal to 0, then the rule is just like, we're starting with the initial value of 0, so you don't have to adjust your exponent at all. Okay, you don't have to transform the function. Okay, so we're going to go ahead, and I see that we're doing an infinite series since we're our ending term is infinity. So we just plug this in. So a to a over 1 minus r. Our a value is 4. Our r value is 0.6, so 1 over 0.6. And since the r value is less than 1, we're good to go, that we can actually apply this, this series. So we have 4 over 0.4, which is 10. All right, our last one is, if I start with the term, I'm going to call this term a sub 0, a sub 1, a sub 2. I tend to find that if we start with the first term being a sub 0, it's a little bit easier to write the equation. Okay, so I'm going to do the sum of n is equal to 0 to infinity, because it's going to go, the terms go on for infinity here. Our initial value is 3, and between each term, we're multiplying by 0.1. So times 0.1. And each term, we're raising it by, we're multiplying by an additional 0.1, so to the n power, okay? So we have a geometric series or a pattern, and my a value is 3, so my initial value is 3, times my r value, which is less than 1. And so I know I can apply my sum formula to this infinite geometric series. All right, so it's a over 1 minus r, giving me 3.3 bar. So this is going to add up to 3 1/3. Okay, so your assignment is on Delta Math.